Assalamu alaikum, my dear students. Welcome to lecture number 15 of CS 317 Operating Systems. This video covers the topic of concurrency. We use chapter number 5 of the William Stallings book. In the last lecture, we explored binary semaphores. We implemented mutual exclusion using semaphores, and we implemented synchronization using semaphores. Let us continue our discussion on semaphores. Implementation of semaphores. It is imperative that the sim wait and sim signal operations be implemented as atomic primitives. One obvious way is to implement them in hardware or firmware. Another alternative is to use one of the hardware supported schemes for mutual exclusion. We shall implement semaphores using compare and swap by enabling and disabling interrupts. Implementation of semaphores with compare and swap. The semaphore that we use is a structure and includes an integer flag. This integer serves the same purpose that the variable bolt served in our example when we talked about implementation of mutual exclusion with compare and swap. First, let us look at sim signal. The critical section is indicated by the blue box in which count and Q of the semaphore are being modified. As long as flag is not 0, the sim signal function keeps busy waiting, comparing flag with 0. When flag is 0, it swaps flag with 1. Compare and swap returns the old value of flag, and the function comes out of the loop to increment count. If count is less than or equal to 0, it unblocks a process from the semaphore's queue. After this, it sets flag to 0. Next, let us look at sim wait. The critical section is indicated by the blue box in which count and Q of the semaphore are being modified. As long as flag is not 0, the sim wait function keeps busy waiting, comparing flag with 0. When flag is 0, it swaps flag with 1. Compare and swap returns the old value of flag, and the function comes out of the loop to decrement count. If count is less than 0, it blocks the calling process in the semaphore's queue. After this, it sets flag to 0. This involves busy waiting. However, the sim wait and sim signal operations are relatively short, so the amount of busy waiting should be minor. Implementation of semaphores with interrupt disabling. The semaphore is the old structure with count and queue. In a uniprocessor, we inhibit interrupts during sim wait or sim signal operations. First, let us look at sim signal. The critical section is indicated by the blue box in which count and Q of the semaphore are being modified. We disable interrupts, increment count. If count is less than or equal to 0, we unblock a process from the semaphore's queue. After this, we enable interrupts. Next, let us look at sim wait. The critical section is indicated by the blue box in which count and Q of the semaphore are being modified. We disable interrupts, decrement count. If count is less than 0, we block the calling process in the semaphore's queue. After this, we enable interrupts. The sim wait and sim signal operations are relatively short, so the time interrupts remain disabled is small. Please note that figure 5.14b has coding error, due to which I have not used it here. Please do not refer to it. People working with and solving problems of synchronization have classified some problems as classical synchronization problems. During the course of this chapter, we will come across a few of these classical synchronization problems. Here I introduce you to the first of these problems, which is called the producer consumer problem, or PCP for short. Problem statement. There are one or more producers generating some type of data, records or characters, and placing these in a buffer. There is a single consumer that is taking items out of the buffer one at a time. The system is to be constrained to prevent the overlap of buffer operations. That is, only one agent, producer or consumer, may access the buffer at any one time. We must also ensure that the producer won't try to add data into a buffer if it's full, and that the consumer won't try to remove data from an empty buffer. We will look at several solutions to this problem to illustrate both the power and the pitfalls of semaphores. The problem has two versions determined by the nature of the buffer. The buffer shared by the producers and the consumer may be of a finite size, or it may be able to grow to any length. The two versions of the problem are called the producer-consumer problem with infinite buffer and the producer-consumer problem with finite buffer. We begin with the producer-consumer problem with infinite buffer. Let us look at the basic assumptions and code. To begin, let us assume that the buffer is infinite and consists of a linear array of elements B. The producer can generate items and store them in the buffer at its own pace. Each time the variable in is incremented. N points to the slot of the array in which the producer will make its next addition. The consumer proceeds in a similar fashion, but must make sure that it does not attempt to read from an empty slot. Each time the consumer takes data from a buffer slot, it increments the variable out. Out points to the slot in which the consumer will do its next deletion. The consumer makes sure that the producer has advanced beyond it, that is, in is greater than out, before consuming. Since the buffer is infinite, both producer and consumer increment their tracking variables in and out. Once a buffer slot is visited by both the agents, it is never revisited. In the figure of the buffer that you see over here, B2, B3 and B4 contain valid data elements. The consumer is now going to consume element in B2 and the producer is going to place a new data item in B5. In our first attempt, we try to implement the producer-consumer problem with infinite buffer using binary semaphores. In the start, we define a global variable n to keep track of the number of elements ready to be consumed. We use a binary semaphore S for mutual exclusion and initialize it to 1. We use another binary semaphore delay for synchronization and initialize it to 0. In the main program, we initialize n to 0 as nothing has been produced yet. and nothing is available for consumption. We begin a producer and a consumer in parallel using the par-begin construct. In the producer's code, we identify the critical section. These are the lines of code that manipulate the global variable n and the buffer. To implement mutual exclusion on the critical section, it is preceded by a sim weight B on S and succeeded by a sim signal B on S. The producer produces an item, acquires mutual exclusion on N and the shared buffer by calling SimWait B on S, appends this item in the buffer and increments N. If N is 1, this is the only item available for consumption. Hence, there is a chance that the consumer has been waiting for it. So the producer issues a sim signal B on delay. Moving out of the critical section, the producer issues a sim signal B on S. In the consumer's code, we identify the critical section. These are the lines of code that manipulate the global variable n and the buffer. To implement mutual exclusion on the critical section, it is preceded by a sim weight B on S and succeeded by a sim signal B on S. The consumer acquires mutual exclusion on N and the shared buffer by calling SimWait B on S, takes an item from the buffer and decrements N. Moving out of the critical section, the consumer issues a sim signal B on S. Then it consumes the data item it has just taken from the buffer. If N is 0, this was the only item available for consumption. Hence, the consumer issues a SimWait B on delay and blocks itself until a producer produces more items. This solution seems rather straightforward. If the producer stays ahead of the consumer, then the consumer will rarely block on the semaphore delay because N will usually be positive. Hence, both producer and consumer run smoothly. Consider the following scenario. We start with N equals 0. A producer comes in, acquires mutual exclusion, appends an item to the buffer, and increments N. Since N equals 1, the producer issues a sim signal B on delay to unblock any waiting consumer. In line 6, the consumer executes a sim wait B on delay, but it is not blocked as a producer has already arrived. So, the sim signal B on delay by the producer is balanced out by the sim wait B on delay by the consumer. The consumer goes on to acquire mutual exclusion, take the produced data item from the buffer and decrement N. N equals 0. The producer comes in, acquires mutual exclusion, appends an item to the buffer and increments N. Since N equals 1, the producer issues a sim signal B on delay to unblock any waiting consumer. In line 14, the consumer checks if N equals 0. Since it is false, the consumer does not issue a sim wait B on delay. The consumer goes on to acquire mutual exclusion, take the produced data item from the buffer and decrement N. N equals 0. No producer comes to append data. However, in line 18, the consumer checks if N equals 0. Since it is true, the consumer does a SimWait B on delay. This SimWait B matches the earlier issued and unmatched SimSignal B by the producer in line 12. The consumer does not block. The consumer goes on to acquire mutual exclusion, take garbage value from the buffer and decrements N. N equals -1. Can you see what is wrong with this code? The code has let the consumer visit the buffer 3 times when only 2 items have been appended to it. This code is wrong. Let us go over what happened. In line 14, the consumer fails to execute the SimWait B operation. The consumer did indeed exhaust the buffer and set n to 0 in line 8, but the producer had incremented n before the consumer could test it in line 14. The action in line 14 should have happened after line 9. The problem arose because right after the consumer came out of critical section, that is after line 9, the producer started working and the remaining code of the consumer was deferred to line 14. The result is a sim signal B not matched by a prior sim wait B. The value of -1 for n in line 20 means the consumer has consumed an item from the buffer that does not exist. Some people may suggest to move the line in the red box inside the critical section of the consumer. Suppose we place the if statement after n minus minus. If n equals 0, the consumer will block in the queue of delay and it will never come out of its critical section, due to which no producer will be able to get into its critical section. Nothing will happen in the system as this will be a deadlock. A fix for the problem is to introduce an auxiliary variable m that can be set in the consumer's critical section for use later on. The if statement stays out of the critical section of the consumer. But now it compares the local integer m to 0 instead of the global variable n. We start with n equals 0. A consumer arrives in the system but blocks in the queue of delay because no production has happened yet. A producer comes in, acquires mutual exclusion, appends an item to the buffer, and increments n. Since n equals 1, the producer issues a sim signal B on delay to unblock any waiting consumer. The consumer unblocks, acquires mutual exclusion, takes the produced data item from the buffer, and decrements n. N equals 0. Consumer sets m equals n. After coming out of the critical section, since m equals 0, the consumer issues a sim wait B on delay and blocks. A producer comes in, acquires mutual exclusion, appends an item to the buffer, and increments n. Since n equals 1, the producer issues a sim signal B on delay to unblock any waiting consumer. Now the solution works fine without any deadlock. If you don't believe it, carry the parallel trace on and finally you will convince yourself. A somewhat cleaner solution can be obtained if general semaphores or counting semaphores are used. We initialize n to 0 and s to 1. S is a semaphore used for mutual exclusion over the shared buffer. The variable n is now a semaphore. Its value still is equal to the number of items in the buffer. The producer makes a data item, acquires mutual exclusion on the shared buffer, and appends the data item to it. Coming out of its critical section, the producer signals on n increments, showing one item has been added to the buffer. The consumer calls wait on n. If n is 0, the consumer blocks. When n is greater than 0 or a sim signal from the producer unblocks it, the consumer acquires mutual exclusion over the shared buffer. After leaving the critical section, it consumes the data item. I want you to construct a parallel trace to convince yourself that this code works perfectly. Here you see the main program in which we do Nothing except beginning the producer and consumer in parallel. So let us do some brainstorming now. This is the solution to infinite buffer producer consumer problem using semaphores or counting semaphores, the code that we just saw. And my first question is, see the two statements in the blue box. What if these sim signals are reversed? Like this. Sim signal N goes up, sim signal S goes down. If you look at the consumer, you will realize that there is no effect on the overall code because the consumer must wait on both semaphores. So no matter which order you generate the sim signals, the consumer requires both signals. Only then it can move into its critical section. The next question is somewhat similar. Look at the blue box again. There are two sim weights. Sim weight N is on top. Sim weight S is at the bottom. This is the consumer code. And the question is, what if the sim weights shown in the blue box are reversed? I mean to say this, sim weight S on top and sim weight N at the bottom. Okay, let us assume that the buffer is empty. So N is 0. Assume that a consumer arrives. The consumer decrements S to 0 and enters critical section. The consumer is blocked on N because the buffer is empty and N is 0. Now, the consumer has already entered critical section, so no producer can enter critical section. The consumer is blocked. A producer cannot get into critical section. This is a deadlock. This is a good example of the subtlety of semaphores and the difficulty of producing correct design. Now we will talk about the producer-consumer problem with finite buffer. The buffer is treated as a circular storage. Pointer values must be expressed modulo the size of the buffer. Valid data items can be found from the slot pointed to by out to the slot just before the one pointed to by in. These are the slots which are shaded blue. In figure 5.12a, valid data items can be found from B2 to B4, both inclusive. In figure 5.12b, valid data items can be found from B5 to B2, both inclusive. So this is a table which tells us what we need to do to implement the finite buffer producer consumer problem. We need to block the producer when the buffer is full. We need to block the consumer when the buffer is empty. Why do we need to do that? Because if the buffer is full and the producer goes on appending more data to the buffer, there is a possibility that the producer will write a new data item on an old data item, and this will result in loss of the old data item, which we do not want. Why do we want to block the consumer when the buffer is empty? We would like to block the consumer because if we do not, the consumer will go and take item from the empty buffer, which would be garbage. If you put garbage into a problem, you get garbage as a result. That is why we do not want the consumer to take anything out of an empty buffer. We need to unblock the producer when an item is removed from the buffer, because this means that there is an empty space available and the producer can go and fill it up with new data. We need to unblock a consumer when item is inserted into the buffer, because this means that new data item is available and the consumer can go and devour it. Let us look at the relevant producer and consumer code. In and out are initialized to 1. N is the size of the buffer, which is an array B. Array index in B goes from 1 to n. Empty buffer is indicated by the condition in equals out. Full buffer is indicated by the condition in plus 1 mod n equals out. The producer can generate items and store them in the buffer at its own pace. If only one slot is empty, in plus 1 mod n will be equal to out. We assume the buffer to be full and do not let the producer append another item to it. So even in a full buffer, one slot is always empty. Each time the variable in is incremented modulo buffer size. N points to the slot of the array in which the producer will make its next addition. The consumer proceeds in a similar fashion, but must make sure that it does not attempt to read from an empty slot. If in and out point to the same slot, the buffer is empty. Each time the consumer takes data from a buffer slot, it increments the variable out. Out points to the slot in which the consumer will do its next deletion. This is a solution to the bounded buffer producer-consumer problem using semaphores. We initialize N to 0, S to 1. S is a semaphore used for mutual exclusion over the shared buffer. The variable N is a semaphore. Its value is equal to the number of items in the buffer. We have a third semaphore E to keep track of the number of empty spaces. It is initialized to the size of the buffer. The producer makes a data item and waits on E. If there is no empty space, E equals 0, the producer blocks. If there is an empty slot, the producer acquires mutual exclusion on the shared buffer and appends the data item to it. Coming out of its critical section, the producer signals on N. N increments, showing one item has been added to the buffer. The consumer calls wait on N. If N equals 0, the consumer blocks. When N is greater than 0 or a sim signal from the producer unblocks it, the consumer acquires mutual exclusion over the shared buffer and takes the data item. After leaving the critical section, the consumer signals on E to indicate a slot has become empty. E increments, and finally the consumer consumes the data item. The main program begins both consumer and producer in parallel. Construct a parallel trace to convince yourself that this code works perfectly. After covering semaphores in such great detail, we now turn towards another method of inter-process communication, which is called message passing. The need for message passing. When processes interact with one another, two fundamental requirements must be satisfied: synchronization, which is enforcement of order, and communication. Processes need to be synchronized to enforce mutual exclusion, and cooperating processes may need to exchange information. Message passing lends itself to implementation in distributed systems as well as in shared memory multiprocessor and uniprocessor systems. Message passing primitives. The actual function of message passing is normally provided in the form of a pair of primitives: send, destination comma message, and receive, source comma message. This is the minimum set of operations needed for processes to engage in message passing. A process sends information in the form of a message to another process designated by a destination. A process receives information by executing the receive primitive indicating the source and the message. Synchronization. The communication of a message between two processes implies some level of synchronization between the two. Obviously, the receiver cannot receive a message until it has been sent by another process. So, messages enforce order. In addition, we need to specify what happens to a process after it issues a send or receive primitive. Consider the send primitive first. When a send primitive is executed in a process, there are two possibilities. Either the sending process is blocked until the message is received, blocking send, or it is not, non-blocking send. Similarly, when a process issues a receive primitive, there are two possibilities. If a message has previously been sent, the message is received and execution continues. If there is no waiting message, then either the process is blocked until a message arrives, blocking receive, or the process continues to execute, abandoning the attempt to receive, non-blocking receive. Thus, both the sender and the receiver can be blocking or non-blocking. Three combinations are common, although any system will usually have only one or two combinations implemented. Blocking send, blocking receive. Both the sender and receiver are blocked until the message is delivered. This is sometimes referred to as a rendezvous. This combination allows for tight synchronization between processes. Non-blocking send and blocking receive. Although the sender may continue, the receiver is blocked until the requested message arrives. This is probably the most useful combination. It allows a process to send one or more messages to a variety of destinations as quickly as possible. A process that must receive a message before it can do useful work needs to be blocked until such a message arrives. An example is a server process that provides a data item to many clients. So the server sends this data in messages to all its clients and the clients wait for the message. Non-blocking send, non-blocking receive. Neither party is required to wait. Acknowledgement. The blocking send waits for the receiver to signal that it has received a message and unblocks on this signal. The blocking receive waits for the message to arrive in a buffer and unblocks on its arrival. Can you tell why the combination blocking send, non-blocking receive is never used? Because if we did employ it, the sender would block for a signal from the receiver. But if the receiver executed the receive primitive before message arrival, it would simply go back to its normal execution without the message, and the sender would remain blocked forever. Hence, this combination is not practical. The non-blocking send is more natural for many concurrent programming tasks. For example, if it is used to request an output operation such as printing, it allows the requesting process to issue the request in the form of a message and then carry on. One potential danger of the non-blocking send is that an error could lead to a situation in which a process repeatedly generates messages. Because there is no blocking to discipline the process, these messages could consume system resources, including processor time and buffer space, to the detriment of other processes and the operating system. Also, the non-blocking send places the burden on the programmer to determine that a message has been received. Processes must employ reply messages to acknowledge the receipt of a message. For the receive primitive, the blocking version appears to be more natural for many concurrent programming tasks. Generally, a process that requests a message will need the expected information before proceeding. However, if a message is lost, which can happen in a distributed system, or if a process fails before it sends an anticipated message, a receiving process could be blocked indefinitely. This problem can be solved using the non-blocking receive. We can allow a process to test whether a message is waiting before issuing a receive. We can allow a process to specify more than one source in a receive primitive. Today we learned the implementation of counting semaphores. We were introduced to one of the classical problems of synchronization, the producer-consumer problem, and its versions. We implemented code for the producer-consumer problem using binary and counting semaphores, and we were introduced to the concept of messages. I understand that many things were really very new and unique in this lecture, so I haven't set you any tasks here. I just want you to go through all the work that I showed you in this lecture and to try to replicate it on a piece of paper so that you truly understand it. Read the book, write your questions on a piece of paper and keep it in front of you during the online session relevant to this lecture. And if you have suggestions relevant to content or quality of this lecture, email them to me. Take care of yourself. Try to enjoy whatever is happening in life. Keep your chin up. Take care. Allah Hafiz.